In fluid mechanics, mass flow and volume flow are among the very first things that we want to quantify when we start studying in flow. So they're obviously very important to us. Mass flow, volume flow, it's really not that complicated. Let's take a look at it together. We write mass flow with the symbol m dot, and it quantifies the amount of kilogram per second that is entering or leaving an area of interest. In the same way, volume flow, v dot, is the number of meters cubed, the amount of volume, per second that is entering or leaving the system. Let's begin with mass flow. To get mass flow, you multiply density, velocity, and area. It's very simple. So if you have a surface of interest, let's say the inlet of a jet engine, it is traversed by the fluid with a velocity v. You multiply density, velocity, and area, and you get the number of kilograms per second that is passing through this inlet. As a formula, very often, mass flow is written like this. Dot m is rho times v times a. But a much better way to write it is when you add a little perpendicular sign next to the v. And a child would know this. When I say a child would know this, I mean this not in a condescending way. Much to the contrary. I mean the child in you knows this already. Let me demonstrate. Obviously, you know you have to turn the area perpendicular to the velocity to get the bubbles out, right? If you have never blown bubbles, or you have not blown bubbles in a long time, then maybe this can be homework for you until the next video. When you blow bubbles, you have a good understanding of the fact that velocity that crosses the area at an arbitrary angle has two components. One of them is parallel to the area and does nothing, and the other is perpendicular to the area and does everything for the bubbles. As a formula then, we write m dot is rho times v perpendicular times a, and by v perpendicular we mean the component of the velocity that is perpendicular to the area. If you want to know the value of v perpendicular, then you need to know the angle between the velocity and the area. If the angle is defined like I represented it here, then you take v times the cosine of the angle alpha. This cosine thing is very uncomfortable to work with, especially once you realize that you can have two angles, one like this and one like that. And the two together can lead up to some uncertainty about how to define and which reference to take. The way to most precisely define it, then, is using a dot product of vectors. For this, we use a vector I, and this vector is a unit vector, has length 1, and it's always positioned to be perpendicular to the area. And v perpendicular is then now the dot product of the velocity vector and this I vector. The dot product of two vectors is a scalar, so a length, so that's fine. We're still landing on a scalar result overall. A few values for mass flow to illustrate now. We start with a human breathing at rest, about 2 times 10 to the power minus 4 kilograms per second. This is 2 10,000ths of a kilogram of air per second on average coming in and out of our body. It's very low. The human heart at rest is a lot more. The heart is much smaller, but pumps a liquid that is much denser, blood, than air. And so we get about 10 to the power minus 1 kilogram per second, 0.1 kilogram per second. If you take a shower, that's about 0.5 kilogram per second. A steam turbine in a power plant is about 50 kilograms per second of steam. A GE90 turbofan at takeoff or a Falcon 9 rocket is about 1,000 kilograms per second of mass flow. And finally, a very large river, say the Nile River, is about 1 million kilograms per second. Let's take a look at volume flow now. We've done all the hard work. The formula for volume flow is exactly the same as for mass flow. We've just dropped the density from it. In the same way as with mass flow, you can express volume flow with a dot product of the velocity vector and the unit vector that's perpendicular to the area. So you see the relationship between the mass flow and the volume flow is very simple. You only have 1 over rho in between the two. This is a hair dryer. Some people use this to dry their hair, I suppose. I don't know what to do with this, but that's not the topic. This machine has an inlet and an outlet. It receives the air from this side. I'm sure you can have the intuition that it doesn't accumulate or deplete air from the inside while it's working, so that all of the air at the inlet is going to be found at the outlet again. The properties at the inlet are very different from the outlet. You can see, I'm sure, that the area is larger at the inlet than outlet. The density is also larger because the air is cool when it's coming in, and it's going to be hot when it leaves. And I'm sure the velocity would be different if we measured it. Here's the thing though, a very important principle in fluid mechanics. When we say all of the air at the inlet is to be found at the outlet, what do we mean exactly? We mean mass flow and not volume flow. So, very important principle in fluid mechanics. We say that mass is conserved. Number of kilograms per second entering this is number of kilograms per second exiting it. But equally important, volume is not conserved. This machine creates volume. The volume flow at the inlet is much smaller than the volume flow at the outlet. To sum up then, mass flow, number of kilograms per second entering or leaving an area of interest. Critically important notion. Start studying something, calculate the mass flow. It's a very easy equation to use. Density times component of velocity perpendicular to area times area. And it gives you a good idea of what is happening. Compare inlet mass flow with outlet mass flow. Are they not the same? Did I make a mistake? Is something happening in there that I didn't see before? That's an excellent start. So that's a good first look, I think, at the notion of mass flow and volume flow in fluid mechanics. Take some time to work with it. I hope you'll be able to make good use of it, and I'll see you in the next video.
Hi, I am Olivier Kleine and I'm recording a video course in fluid mechanics. If you find this video useful, check out the rest of them at learnfluidmechanics.com. I hope to see you there. Take care.